Hello, everyone. I'm Eunkyoung from Yonsei University. It's great to share our work on energy-saving smart windows with you all. Smart windows present a core solution to reduce energy consumption through windows. They range 30 to 50% of the energy used to heat or cool building. It can be designed by electrochromic principles, where optical changes can be induced by the application of electricity for the redox switching of EC material. EC window provides a simple window structure having electrode, electrolyte, and electrochromic materials. In this presentation, I would like to focus on conjugate polymers for EC window due to their easy synthesis and film preparation. Moreover, the color of conjugate polymers are easily tunable. These EC windows can be integrated with an energy harvesting system to switch light transmission through the window. For example, solar cells can be attached in a circuit connected multi-cell structure or optimally one cell with multifunctional materials. Obviously, the efficiency of these cells are not high enough to provide a continuous power for electrochromic window. So to integrate EC window with energy harvester, bistability of color at voltage of state is necessary, by which we do not need energy supply to keep the colored or bleached state. Of course, low working voltage would be necessary, and it would be beneficial to have energy storage and reuse of switching electrochemical energy. And also simple integration would be necessary to mount this system on a window. Fundamentally, this bistability of color at voltage of state relates to the spontaneous self-bleaching or self-coloration. And the self-coloration normally occurs at this interface between polymer and the electrolyte, where the ions are transferred to the electrolyte. Self-bleachings could occur when polymer has a high E HOMO level compared to this Fermi level of electrode. So it's important to control their HOMO energy and also blocking of ion transport at voltage of state. To control the HOMO energy level of electrochromic polymer, we can utilize side chain engineering, where we introduce electron deficient group or structurally bulky group to get this higher oxidation potential, namely to lower the HOMO energy level. Among those, this product series with bromide substitution give high coloration, and when it is neutral, and when it is oxidized, it gives almost no observance at this visible range, giving high color contrast. So it is quite often used in our system. The optical memory of the colored state for this product series with a bromide give a very stable without any transmittance change. And as we compare here over the series of polymers having different HOMO energy level, these transmittance change at voltage of state are highly dependent on their HOMO energy or oxidation potential. Namely, the high HOMO polymers have the large change in this transmittance. So in this way, we can control this optical memory at the colored state. On the other hand, the self-coloration could not be controlled in typical electrolyte. And already we proposed that this is originated from dopant ion transfer toward the electrolyte. So if we utilize a ion blocking layer, it could sustain this dopant ion in the polymer. So we use ionic liquid instead of organic solvent. Then we could have a very stable transmittance at this voltage of state. So to get this bistability, we can see that this interfacial electron transfer as verified from the plot of this overpotential against this E half, or dopant ion transport. Here the plot for this rate constant for dopant ion against this two different electrolyte. And you see that this dopant ion, the rate for dopant ion transport were minimized for all polymer in our study. However, this dopant ion transport was significant in typical TBAP dissolved in this organic solvent. So to get this bistability, it was concluded that the low Homo energy polymer and ion liquid are necessary for EC material and also for electrolyte respectively. So we were able to get quite stable. Let me see if I can show this video. All right, so, okay. So to get such a bistability, we need to have this series. So among those, we adopt this PRBR based window, and it shows that high optical switchability. And more importantly, at voltage of state, it sustained this transmittance at both colored and bleached state for a couple of hours. That saves significantly the energy consumption of EC window. Then to lower the driving voltage, it is necessary to balance the charge between the working and the counter electrode. As we know from this non-stick equation, this potential distributed at the polymer electrode are highly dependent on this counter electrode material. So if we utilize titanium dioxide as a charge balance material, then the thickness of titanium dioxide nanoparticle would affect this potential, voltage distributed at this working electrode. That means we can reduce this applied voltage by controlling this thickness. Indeed, with about 2.6 micrometer thick titanium dioxide layer, the working voltage was reduced to 1.8 volt from 2.8 volt. In that case, there is no charge balancing layer. So about 1 volt was reduced to reach transmittance change of about 70%. Since we were able to reduce this working voltage, the cyclability of the EC window becomes longer because we reduce this unwanted electrochemical process. Then this bistable low voltage working EC window could be integrated with energy harvesting system. But most of these dye sensor solar cell harvest UV and visible range, but transmit NIR range. So in order to harvest this NIR range, we utilize a photosummer system that can heat pyroelectric and the thermoelectric system. So among those photosummer material, we utilize PDAT system because it's well known that PDAT has high photosummer efficiency, and also it can be easily made on top of this PDAT pyroelectric and also thermoelectric system through the solution coating process. So this is the output power from pyroelectric and output voltage from this photosummer thermoelectric system. And it can be seen that with about 100 milliwatt NIR laser, it can generate voltage of around 200 millivolt instantaneously. And over the time, thermoelectric system shows a voltage output. And interestingly, with these two systems integrated, the voltage output is always larger than the single system. Lastly, if we combine this photothermally activated pyroelectric and thermoelectric system with the photovoltaic system, like a dye-sensitive solar cell, this photo conversion efficiency is increased about 20%. And this output voltage is also increased for small single cell or the large cell having four small single cells made of the four single cells. And these large cells generate 2.75 volt, which is sufficient to operate the electrochromic window. Indeed, with a one shot of this photon, solar energy, it can operate this electrochromic window from colored or transparent state. And since this is the electrochromic window, it can sustain this colored state without supplying energy or voltage for this colored state or bleached state. So it's not necessary to supply any energy for the maintaining of this color. Only the energy is necessary to switch this state. Having such a circuit-connected photo-rechargeable EC window, we now explore a single device system, considering that the counter electrode of EC window for low voltage driving window is composed of a metal oxide like a titanium dioxide nanoparticle. It could function as both charge balancing as well as photoanode if dye is absorbed, as we know this photoanode from titanium dioxide that was absorbed with a dye. So our proposal to get this photo-rechargeable electrochromic window is based on this photoanode and couple with this electrochromic layer in the presence of redox active ionic liquid. So open exposure to light, dye excited and generated electron, which can be harvested in the conduction band of titanium dioxide. And then this oxidized dye can be regenerated by the redox active ionic liquid. Then the photo voltage generated at the titanium dioxide layer can can trigger the photo coloration of this transparent EC window. So it can be harvested. This harvested energy can be used for this photo coloration. Indeed, this gives a photo voltage from the one of this single cell structure. On the 100 milliwatt, it can generate over 1 volt. And this voltage over 1 volt, of course, as corresponds to the voltage application at about -2 volt. And even if the photo voltage of 0.7 volt, it corresponds to the application voltage of -1 volt, which is very sufficient to reduce electrochromic polymer. So with one shot, this transparent electrochromic window changes color toward a dark color. The bleached state normally has about 85% of transmittance. In this colored state, it's about 98%. 2% means that about 98% of light can be blocked from this window. And from the spectral comparison, EC operation gives colors about this. And even for the photo coloration, this observance is higher. So make sure that this photo coloration is quite useful. And we can compare the conventional one made of tungsten trioxide and titanium dioxide, or molybdenum oxide and titanium dioxide system. This photo coloration efficiency is very high in our system, proving that this could be utilized for this photo coloration system. So in summary, we demonstrate the solar or photo-powered energy harvesting electrochromic window. To reduce energy consumption of an EC window, we achieved the bistability of color through this low homo polymer and electrolyte containing ionic liquid to form stable electrical double layer. Working voltage was reduced about 1 volt by achieving charge balancing between the electrodes to drive the EC window at low photovoltaic system. Annihilate typically transmitted from the typical Dyson solar cell was harvested by photothermal conversion that hits pyroelectric and thermoelectric layer to generate a higher photovoltage for EC switching in a hybrid harvester. Charge balancing layer at the counter electrode and also electrolyte were modified as photoanode and redox active 1, respectively, to achieve energy harvesting and electrochromic in a single cell device. So up to now, we have about 10-inch size of windows. So our future work will concentrate on the scalability of this window to be realized in a EC window. With this, I would like to thank the people who worked for EC window and the photoelectrochromic EC window and the bistability mechanism in our lab. And also thanks to the Global Research Laboratory funded by Ministry of Science, ICT, and Future Planning of Korea. Most of all, thank you for your attention.